Welcome to lecture 2 of week 7, the urinary system. In part 1, we talked about the macroanatomy of the kidney and the ureters and the bladder. And then I said in part 2, we would really zoom in on that nephron that sits out in the cortex. And we have millions of these nephrons in our kidneys, and they are the ones who do all of the filtration of the blood, and that creates urine. So we're going to zoom in on that nephron here. So just to recall the vasculature. So remember that oxygenated blood comes into the kidney through the hilum and then comes out to the cortex. This is where filtration will happen out here. And then deoxygenated blood will flow back out of the kidney, out of the hilum, and then back through the inferior vena cava, back to the heart. So remember that our renal arteries are branches of the abdominal aorta, and our kidneys actually house 15 to 30% of our cardiac output at any time. So the kidneys are highly, highly vascular, as you probably noticed from part 1. And that's important because our blood needs filtered constantly to do all those functions that the kidneys are designed to do. So just to kind of recap, we came in the renal artery. Renal artery will divide into segmental arteries in the pelvis area. Then the segmental arteries will divide into interlobar arteries, which will sit in between all of the renal pyramids here in the renal column space. Each of those interlobar arteries will split to arch over the top of each pyramid. Those are called arcuate arteries. And then the little tiny branches off of the arcuate arteries are going to be our cortical radiate arteries. And that's where we stopped in part 1. But now we're going to zoom in on this area here. So my best analogy that I tell my students on ground is if you've ever seen the movie How the Grinch Stole Christmas, especially the Jim Carrey version, they have that snowflake, right? And they zoom into that snowflake, and inside that snowflake, there's this tiny little village of tons of stuff going on, right? Whoville. So that's kind of my relation to this. So we're going to zoom in here on the cortex, and there's going to be a lot going on in there at the microscopic level. So if we zoom in here, just to kind of orient yourself with this picture, this is what we're looking at. So here's a pyramid, here's the papilla down here, here's going to be our minor calyx down here, here's our cortex. So if we zoom in, here's our arcuate artery, okay, and then we have all of these little cortical radiate arteries here. And look on the end of this cortical radiate artery. Now we have this thing attached to it. That's something that we couldn't see from the macro structure. That's going to be our nephron. And so you notice that there's some vessels intertwined here. There's also these yellow tubules. So remember that there's a vascular pathway for the kidney, and there's also a tubular pathway of the kidney. Blood comes in, what comes out is blood through the vascular pathway, venous blood, but also urine. And so we have these two different pathways, and where all that's going to happen is in this little ball spherical shaped structure called the glomerulus. So that's where we're going to zoom in here. So from that cortical radiate artery, we're just going to add some branches here. So after the cortical radiate artery, now we enter this glomerulus via something called the afferent arteriole. Afferent arteriole. Okay. Now, inside this little sphere here, there's capillaries. Those are called glomerular capillaries. That is where the majority of filtration is going to happen. And here is where our beginnings of urine is going to be formed. It's going to be called filtrate until it leaves the kidney. But this is where all that's going to start. So from the glomerulus, we will have a vessel leaving the glomerulus that will eventually turn into venous system. But we also have a tubule leaving the glomerulus. So you can imagine that in that glomerulus, most of the filtration is going to happen. The wastes are going to go through the tubular system, and the clean blood, okay, it's not totally clean quite yet, but it's pretty clean, is going to exit via this efferent arteriole, EFF. Okay. So just to add on to that pathway that we covered in lecture 1, we're coming from the cortical radiate artery that turns into something called the afferent arteriole. That afferent arteriole is going to enter the glomerulus. This glomerulus, which we'll talk about here in this lecture, has capillaries called the glomerular capillaries. And then if we just stick to the vascular pathway for now, We're going to exit, blood will exit the glomerulus via the efferent arteriole. Okay. Now, the next step is something called peritubular capillaries or vasa recta. There are two different types of nephrons here, which I will go into the next slide or so. Notice where they're located. This nephron is located very out towards the cortex. This nephron dips down into the medulla. Here, okay, so this structure is mostly in the cortex. That is called a cortical nephron. Okay, this one is called a juxtamedullary nephron. Juxtamedullary nephron, and that one is going to dip down into the medulla. So the next step in our vascular pathway depends on what type of nephron you are. If you are a cortical radiate nephron, the capillary bed that comes next is here. It's intertwining with this kind of, it looks like a tangled mess, really. This is called peritubular capillaries. Peritubular meaning around the tubules. So there's going to be a capillary network here after the efferent arteriole, called peritubular capillaries. That's if you're a cortical nephron. If you're a juxtamedullary nephron, here's our afferent arteriole, here's our efferent arteriole, and then here's our capillary network that dips down into the medulla. This is called vasa recta. Okay, vasa recta. These two capillary beds are important for a lot of reasons that we'll go into in the next lecture, but just know that depending on what type of nephron you are based on location, cortical nephrons, if you're out towards the cortex, you're going to have the next stop is going to be this peritubular capillary network. If you are a juxtamedullary nephron, you're going to be vasa recta. Then everything just kind of works its way back out of the kidney. So from the peritubular capillaries, then we're going to enter here, and it's kind of hard to follow. I'll show you a better picture in the coming slides. But now we're here in the cortical radiate vein. So now we're exiting this region. Cortical radiate vein dumps into the arcuate vein, right? And if we're looking at this one over here, we are going to have our dumping into here, into the cortical radiate vein, or excuse me, arcuate vein, into interlobar vein. And then if we zoom out, remember that there are no segmental veins, but these interlobar veins are going to dump into our renal vein, which will then go into our inferior vena cava, and that blood will go back to the heart to be reoxygenated again in the lungs and then be pumped out. Okay, so that's our vascular pathway. This picture is from your book. Basically, this shows in at the nephron level and then out. So this is a order of pathway that you are going to need to know inside and out. So I would practice either writing it down or talking out loud about it, that this is kind of what this is all going to look like here. Again, I mentioned that there are two types of nephrons. There are cortical nephrons out here, and there are juxtamedullary nephrons here. The nephrons basically work according to the sympathetic nervous system. So nephrons work according to blood pressure, and we're going to talk about blood pressure in this in the coming slides. But basically how things are filtered is dependent upon the pressure from blood pressure. Remember, filtration from week 1 is basically the separation of substances in a solution, right? Separating solute from solvent based upon a pressure. And so this pressure in this case is going to be from blood pressure. It's a passive process, so there's no ATP involved, but this is going to depend upon blood pressure. Now, most of the nephrons are going to look like this. They're going to be cortical, which means that most of them are going to be out towards the cortex as much as possible. Juxtamedullary nephrons is about 15% of the nephrons. Those are going to extend down into the medulla. Now, why do we have both? Well, there's millions of these little guys in each kidney. And so they have to kind of be staggered like this in order to fit as many possible as we can inside that kidney. Now let's talk about this glomerulus. So we're talking about this little spherical shaped structure here. So we enter the glomerulus via this afferent arteriole. We have these capillaries inside the glomerulus called the glomerular capillaries, and then the blood exited via the efferent arteriole. I also mentioned that there's a tubular pathway here because in this area is the separation from blood from urine, or the beginnings of urine rather. So there's this capsule. Notice that this whole structure is encased by a layer of cells. Okay, this is called the glomerular capsule, or some people may know that as Bowman's capsule, same thing. Then we have the glomerulus itself, which is made up of these capillaries, these glomerular capillaries. And there's this space in between the two. Okay, so you can imagine that as blood enters these capillaries and filtration happens out of these capillary walls, the wastes and what will become urine will enter this space and it will all drain out through the tubular pathway and become urine. The clean blood will just circulate back out the efferent arteriole, but those wastes will be left in that capsular space. This whole thing with the capsule plus the glomerular capillaries is all called something called the renal corpuscle. So this whole thing all together is called the renal corpuscle. So blood enters this afferent arteriole. Something I want you to note is that the afferent arteriole has a larger diameter than the efferent, and we're going to talk about why. I believe in this lecture. And these capillaries, if you can remember from the types of capillaries that we had, there were continuous capillaries, fenestrated capillaries, and sinusoidal capillaries. And remember that the continuous capillaries had the tightest junctions, so things couldn't pass through. And the sinusoidal capillaries had the largest spaces between the cells, so large objects could pass through those capillary walls. These are fenestrated, which are kind of the middle of the road, so things can exit through the cells that make up these capillaries. And I'll show you a zoomed in picture in a second. So small things like sodium and chloride and potassium and water can all pass through these capillaries and enter this capsular space. And that's going to start to form what we will call urine. So again, two exit points at this point, a tubular exit point and a vascular exit point. Our vascular exit point will be the efferent arteriole. Our tubular exit, which I'm going to get to at the very end of this lecture, we're going to call that the proximal convoluted tubule. Okay, we're going to talk about that more in a little bit. This is a 3D micrograph. This is really cool. So here's our glomerulus. Here's our capsular space here. And then our tubules, this is a cross section. So you see lots of holes here. Those are going to be all of those tubules, that kind of tangled mess that we saw in the previous cartoon. So let's go over that order one more time here in this picture. Everything's kind of stretched out a little bit better. We come into the kidney, and let's start with the arcuate artery into cortical radiate artery. Branch off the cortical radiate artery is our afferent arteriole that enters our glomerulus. Filtered blood will exit the glomerulus via the efferent arteriole. And notice that this is a juxtamedullary nephron because it's dipping down lower into the medulla than the other one. So this is going to enter a network, a capillary network called vasa recta. Okay. And then that will enter our arcuate vein, out the interlobar vein, and then out the kidney. If we are a cortical nephron, here's our arcuate artery, cortical radiate artery, afferent arteriole, glomerular capillaries, efferent arteriole, peritubular capillaries, and then cortical radiate vein, arcuate vein, and then out the kidney. All right, so this glomerulus, there are different layers of the capsule. There's a parietal and visceral layer. So you can imagine that the visceral layer is the inside layer. The parietal layer is the outside layer. We don't need to focus too much on that, but I do want to note that this visceral layer that covers these capillaries has little cells here called podocytes. They almost look like little, I don't know, spidery looking things, kind of like a bug almost. So these podocytes have pores between them on the capillary wall, and that allows things to exit. That makes those fenestrations in the capillary wall so that things can filter through. Those podocytes are important for a lot of like stimuli detection, like blood pressure and things like that. We're not going to get into too much detail with that, Your book does, but those podocytes do have more function than just providing the fenestrations that are on these capillaries. So let's recall that a capillary bed, blood enters an arteriole, goes into a capillary bed, and then we exit via a venule. And so filtration, just like in our capillary beds that we talked about in the blood module, it's driven by pressure, in this case, blood pressure. And so I also want to remind you that there's something called colloid osmotic pressure. So remember that water is in this capillary bed, right, in these vessels, and it will leave into the tissue via osmosis because the water concentration is much higher in the blood than it is out here in the tissue. Also remember that protein is too large to cross this wall, right? So protein is going to hang out in the capillaries. Well, water's out here. Remember that water is attracted to higher solutes, and so water will actually be drawn back into the vascular system because it's going to be attracted to those proteins. So it'll first be filtered out, but then it will be drawn back in according to balance out how much protein is in the blood. And that attraction is called colloid osmotic pressure. So that's something to keep in mind here moving forward. So how does filtration occur? Well, here's our capillaries here. We have a blood pressure coming in this arterial system, right? And this blood pressure will force small molecules out of the capillaries into this capsule space. Water, small molecules, ions, your glucose, your sodium, your chloride, things like that will all enter this capsular space, water. Large molecules cannot pass. So proteins are going to stay in these capillaries, and that's going to be important here for the draw of water. So filtration is going to force small molecules into the space that will eventually contribute to urine, and then protein will stay inside here. So the beginnings of urine is here, and that is called glomerular filtrate. We don't call it urine yet because there's a lot more filtration that's going to happen downstream, but this is going to be called glomerular filtrate. It's composed mostly of water and solutes, small solutes. Some of them are listed right here. So again, here are those pores, right? Those fenestrations. Our podocytes are also providing slit pores here, fenestrations, for small things to exit the capillary into the capsular space, all driven by blood pressure. So things that stay in our bloodstream that cannot filter through, right? Blood cells. So our red cells, white cells, platelets, things like that. Certain plasma proteins, so antibodies, antigens, things like that. Larger anions, proteins, and basically most molecules greater than 8 nanometers. In our capsular space, we'll have our water, electrolytes, glucose, amino acids, a lot of metabolites here. So here is our capillary, and then here are our podocytes that cover that capillary wall. And so things will pass through here and be filtered out. So if something does pass through the capillary here, let's say that a larger molecule makes it through this capillary, it probably won't make it through the podocyte slit pore. And so therefore it'll go back this direction and be held up in the bloodstream. And this, I want you to kind of think about what's normal to find in your urine and what's not normal to find in your urine. So do you want blood cells in your urine? Do you want to basically urinate blood? No, right? And so those things need to stay in your capillary system. They should not enter the capsular space to form urine. Here's your clinical correlation, proteinuria. Protein is not something you want to find in your urine either. It is filtered into the filtrate at the glomerulus in proteinuria. Mostly protein should stay in the vascular capillaries, right? But when we have certain pathologies that are wrong with the kidney, wrong with the body, that protein will creep through here and end up in the urine. That is abnormal. So something that it could be caused by is lack of blood flow to the kidneys. So a lot of time athletes who are constantly activating their sympathetic nervous system when we activate our sympathetic nervous system, we actually kind of shut off our kidneys because we want to shunt the blood towards our muscles and our breathing mechanism to drive those activities rather than drive the activity of making urine. Our body doesn't see that as important during our sympathetic response. During a lot of like athletes, performances, things like that, our kidneys become a little bit hypoxic because they're not getting as much blood perfusion. And so then they become kind of leaky. And so protein can creep through. Also, blood can creep through as well. Certain things can cause this. Glomerulonephritis is basically the inflammation of the glomerulus and the kidney. Remember that during an inflammatory response, the capillary becomes leaky, right? It becomes inflamed, and that allows leakiness because we want white blood cells to exit the capillary and go into the tissues to the site of infection, right? And so they become very leaky, very permeable. Well, if the vessels of the kidney are becoming permeable, a lot of these larger things can now exit, whereas they couldn't before. And so that's also a reason how protein gets out. Diabetes, and a lot of diabetics, we talk about high blood pressure. And remember that high blood pressure can be caused by higher solute concentration in the bloodstream, in this case, higher glucose concentration. And so that increases your blood pressure. Well, your kidneys have all these very teeny tiny little vessels in it, right? And so if you increase the blood pressure of the body, you're increasing the pressure in those little bitty vessels. And that can be very harmful to a very tiny vessel, a very tiny arteriole. And so if we damage that wall of that capillary due to high blood pressure, well, now we have things passing through that shouldn't. And then immune disorders, that just kind of goes with the permeability of the capillary during an inflammatory response and things of that nature here. So a lot of people with high blood pressure, diabetics, those type of people end up having renal failure or kidney failure due to the damage of those blood vessels in the kidney. Lots and lots of blood vessels in the kidney, very tiny, very prone to damage. So how does this all happen again? So our glomerulus creates a fluid called filtrate. That filtrate enters the glomerular space here and is going to travel down that proximal convoluted tubule. So that's going to go down the tubular system. Now, where does the rest of the blood go with the protein and the water? That's going to head back into circulation and either it's going to exit the efferent arteriole and then either go into the vasa recta or the peritubular capillaries. Now, during tubular pathway, which we're going to get into here, we have something called reabsorption and we also have secretion. So filtration happens here. After that, we have something called reabsorption, and then we also have secretion. And through that, we are going to take out and put in more substances into that tubule. And by the end of that tubular system, we will have what constitutes urine. We'll get into that here more shortly. So just to kind of recap on these pressure gradients in filtration. Filtration is passive. It's driven by a pressure, in this case, blood pressure. The afferent arterial diameter is greater than the efferent. What does that imply about the pressures in those two vessels? So remember that the wider the blood vessel, the less pressures in that vessel. So that afferent arteriole is wider to accommodate higher pressures coming in to the glomerulus so that we don't damage that. And blood will end up backing up in these capillaries because it cannot exit out this vessel as fast as it entered because this one's a little bit narrower. That's beneficial because the longer the blood sits in here, the more filtration can happen. And we really want super clean blood after it leaves the glomerulus. So there's a few pressures here, and this is how we figure out how filtration actually happens. So there's this glomerular hydrostatic pressure. This is the greatest pressure that there is. This is the pressure of blood pressure pushing substances from the capillaries into the capsular space. Okay, that's glomerular hydrostatic pressure. Blood pressure forcing molecules from these from these glomerular capillaries into this capsular space. That should be our greatest pressure. We have some opposing pressures though, working against that, and those should be a little bit less than the outward pressure. So remember that we still have proteins hanging out in these capillaries. So those proteins are going to attract water. And so that's going to create an osmotic pressure where water is going to want to go back into the capillaries. Seems a little counterproductive, but that's called plasma colloid osmotic pressure. So there's going to be some proteins creating that plasma colloid osmotic pressure, drawing water back into the capillaries from the capsule. And then as we filter more out into this capsular space, the fuller it gets, the more pressure it will have. And so the fuller it gets, it will create this capsular hydrostatic pressure. Hopefully that pressure is very small because everything will drain here out the proximal convoluted tubule, unless something's blocking that pathway like a kidney stone or something like that. So ultimately, the pressure out of the glomerulus into the capsule should be greater than the two opposing pressures forcing contents back into the capillaries. And that's how we get our net filtration pressure of 10 millimeters. Our glomerular filtrate is very high. Now notice that our urine is very low compared to how much glomerular filtrate we create. Why? A lot of reabsorption happens. So a ton of things are filtered out in that glomerulus, but as we're going to see is that later down the tubular pathway, a lot of these substances are reabsorbed back into the bloodstream, depending on what our body needs. So if our body's low in sodium, a lot of that sodium that was filtered out initially will be reabsorbed back into the bloodstream. And so we actually don't urinate a whole lot per day compared to how much our glomerulus actually filters per day. Remember that our kidneys receive about 25–30% of our cardiac output, so lots of blood entering this. Normal GFR, which is glomerular filtration rate, so that's how fast that filtration happens in the glomerulus, is about 120 to 125 milliliters per minute. That's quite a bit. And so ultimately, we are filtering about 180 liters in 24 hours, but we're only urinating up to 2.5 of those liters in 24 hours, which means about 177.5 liters is reabsorbed back into our bloodstream, which is fascinating. Our entire blood volume is filtered 60 times per day. So think about that. That's crazy. Now, as our net filtration increases, our GFR increases, and this glomerular filtration rate has to be at a homeostatic set point. We do not want it to filter too much or too fast or too slow. It needs to be at that happy set point. So, but the more filtration we have, that means that we're at a higher filtration rate. Okay. So what would happen to GFR? What would happen to the rate of filtration if our afferent arteriole was constricted or contracted? So here's our afferent arteriole. So we have blood coming into this glomerular capillary area, which this is where GFR is measured. So if we make this diameter smaller, what will happen to the rate of filtration in here? It's going to decrease. Okay, the less blood you have coming in, the less filtration that we can have. That should just be kind of logic, right? What happens if we constrict our efferent arteriole? So blood cannot leave the glomerulus as quickly as it came in. That should increase our GFR, right? So the longer that the blood sits in here, the higher the filtration. Okay, so the more blood that enters, the higher the filtration, the slower it takes to exit, the higher the filtration as well. Vasodilation would produce opposite effects. So let's see what would happen. So if you expand this afferent arteriole, if you vasodilate that, you're going to have a ton of blood entering this glomerulus. And that's going to increase our GFR. So the more blood that enters, the higher the filtration rate. Now, that could be a good or a bad thing. We're going to talk about the scenario when it's a good thing, but the higher the filtration rate, the less chance that you have that this is going to filter properly, because it's going to be going so fast that it might not filter everything out that it needs to. So kind of a double-edged sword here. But our glomerular capillaries have a relatively high pressure, and they need to, because we need to favor that filtration into this capsular space. And so our plasma protein, which is in the capillaries, will oppose filtration. And so that will attract that colloid pressure, attract water back in. That increases our blood volume. So let's back up for a second. So if you have our blood volume here, which is high in water content, right? Coming in here, and a lot of that water is filtered out into this capsular space because of osmosis. What happens to our volume? It goes down, right, in our capillaries. And that means our pressure goes down as well. But some of that water will be reattracted back into the capillaries because of the protein attraction. That will then raise our blood volume and raise up our blood pressure again. Okay, and that allows more things to be filtered out. So this has to be greater. This glomerular pressure has to be pretty high in order to favor filtration. So we need water. We need a lot of water in our capillary network, essentially, to favor filtration. Later down the tubular pathway, we'll see where water actually contributes to our urine output, because urine is mostly water. So we need to put water in here somewhere along the pathway. But a lot of water is going to be reabsorbed into the capillaries here in the glomerulus due to that attraction of protein. What would happen if our plasma protein concentration decreased? So what if we didn't have a lot of protein in these capillaries? Then what would happen? Then we wouldn't have as much water going back into our capillary network, right? We'd have a lot of water here that's going to go into our filtrate. That's fine, but then what can we say about blood volume and blood pressure here? It's going to be low, right? The less water that we have in our blood, the less pressure. And so we're going to have less blood pressure leaving the kidney then. Good and bad things. There's different pathologies that contribute to all of this stuff. So GFR, so we have that hydrostatic pressure in our capsule. So I'm talking about the pressure that's in here. Remember, this was our lowest pressure, but the fuller that capsule gets, the higher pressure it's going to exert and force things back into the capillary. So what happens if we have a kidney stone, right? What if there's a stone right here so that this filtrate cannot exit this glomerulus? Then what happens? This pressure is going to be greater and greater and greater. And that filtrate is going to go back into the bloodstream, and your kidneys are not going to be filtering very well. Okay, so there's a lot of different ways that we can measure. And this one is just here showing hydronephrosis, which is going to be a lot of fluid in the kidney. Basically, what we have is a buildup. So here's our kidney stone here in our proximal ureter, and we have this buildup of fluid, buildup of urine filtrate here. Because it cannot exit the glomeruli. That damages the glomeruli, right? And then they become more permeable. If you've ever had a kidney stone, you probably have protein in your urine, you have blood in your urine, you have all those things in your urine because that glomerulus is being damaged by that opposing capsular pressure. So that can be measured in a blood test. We can measure GFR, we can measure blood urea nitrogen, which is a waste product of amino acid breakdown, and then also creatinine, which is also a waste product of amino acid breakdown. So those things are measurements that we can take in the blood. Those things should be in our urine, be excreted in our urine to a certain degree. But if they are reabsorbed back into our bloodstream, that is not good. That means our kidneys are not doing their job. All right, so we're going to talk a little bit about how our kidneys regulate GFR. They're very smart little organs, but the two things that I need you to kind of wrap your head around right now is a high GFR. If your GFR is too high, right? If our filtration rate is too high, fluids are moving through that glomerulus too fast, and we cannot properly reabsorb things like the water. Okay, but if that rate is too low, those fluids are not being filtered quickly enough. And so our urine output is going to be diminished. And in addition, we're going to have reabsorption of wastes from that capsular space back into the glomerulus. So you want a happy medium. You want a spot where essentially wastes are being filtered out of those capillaries, but don't have the chance to be reabsorbed back into the bloodstream. We want them to be in that capsular space and continue down the tubular system to form urine. Our kidneys accommodate blood pressure pretty well. It's called autoregulation. This maintains our fluid and electrolyte balance independently of blood pressure. So if your blood pressure is too high, the reason why people with high blood pressure don't always have kidney damage is because the kidneys are kind of doing their own thing to accommodate and save themselves from that high blood pressure. Same thing if it's low blood pressure. So, for example, if the systemic pressure rises, let's say that your overall blood pressure rises, that stretches your arterial walls. We know that. And then normally our blood vessels in our body would vasodilate, right? To accommodate that high blood pressure, to reduce the peripheral resistance. Well, if our afferent arteriole expands, what's going to happen? If this also dilates, what's going to happen? More blood is going to enter the glomerulus and filtration could happen too quickly. We don't want that. Right? The more volume that enters the glomerulus, the higher the GFR. We don't want our GFR to get too high. So what our kidney does to respond to that is actually constricts the afferent arteriole. So normally all of the other arterioles of our body are dilating. The afferent arteriole is actually going to vasoconstrict so that a high volume of blood does not enter the glomerulus as quickly, and this GFR can be maintained at its rate that it should be for proper filtration. Okay. Now let's talk about the opposite. What happens if our systemic blood pressure is too low? So that's going to be lessened perfusion throughout the body, right? Well, normally, how do our arterioles respond? They're going to constrict, right? If our blood pressure is too low, vasoconstriction will increase the peripheral resistance, and that will increase our blood pressure and bring it back up. So we would expect that our afferent arteriole should do the same. It should constrict. But if we have low blood pressure, that means we have low perfusion, which means that our tissues are not getting enough oxygenated blood. And our kidneys can't handle that, right? So in response, our afferent arteriole is actually going to dilate. So you can imagine if our blood pressure is low here, where we have a low volume of blood out in the body, not a lot of blood would be entering this glomerulus. So if we dilate this blood vessel, we can allow more blood volume to come into the kidney, and filtration can still occur in times of low blood pressure. If that didn't happen, we would not have enough blood coming into this glomerulus, and our GFR would be severely decreased. We would not have a lot of filtration happening. So basically, you have to think opposite now. So what's happening in the body vessels, actually the opposite happens in the kidney. That's called autoregulation. That is kind of how our kidneys kind of self-regulate themselves. No matter what's going on outside in the other vessels of the body, the kidneys will still maintain their job. So a couple mechanisms how this happens. So the one that I was kind of talking about is called myogenic mechanism. So that's caused by the sympathetic nervous system. So we know that blood pressure is controlled by the sympathetic nervous system. And so we have that vasodilation and vasoconstriction. Something else about hypotension, so this is going to be low blood pressure. Not only does our afferent arteriole dilate to allow more blood in, but our efferent arteriole in low blood pressure and hypotension will actually constrict. And that will allow the blood, what volume of blood there is in here, to kind of marinate in here for a lot longer, to have that filtration have its fair chance at happening, because we don't have a lot of blood to work with, right, in the first place. And so we need to filter that as best as possible. So this efferent arteriole will actually also constrict in low blood pressure environment. The other type of autoregulatory mechanism is called tubuloglomerular feedback. And our tubular system has a lot of sensory cells. Here, all these little tan colored things are tubules. They have sensory cells. I'm not going to make you know them for this class. That's called macula densa if you run across it in your readings. But essentially, there's some sensory cells in the tubules that detect the composition of the urine filtrate and if it's okay or not, right? And so if there is a high volume of filtrate, we are going to lower that GFR, because that means if there's too high of a volume, if there's too much filtrate in those tubules, that means that our GFR was going way too fast and we filtered too much stuff at once. So what's going to happen is our afferent arteriole would be constricted slightly. And if our afferent arteriole is constricted slightly, remember, less blood can enter, and that will lower our GFR. That's our homeostasis. So if we have too much fluid here in the tubule system, too much fluid, that means filtration happened way too much, way too quickly, probably too. And that means that too much blood was entering here and moving through here too fast. The pressure is probably too high. And so in order to accommodate that, remember that normally if the pressure is too high, we dilate, but the kidney does autoregulation. And so this afferent arteriole would constrict. That would lessen the amount of blood coming in order to only do enough filtration to accommodate our homeostasis. And it would be the opposite for a low blood pressure. So that's called a low filtrate volume. So it could be the opposite. If there's not enough filtrate in the tubules, then we would do the opposite effect. So these are two different ways that our kidneys control their own GFR. These images are from your book. This just kind of goes through again images of what I was just kind of talking about. Now, I've been talking about this tubular pathway. What is it, right? This picture is all of the tubules without the blood vessels. So what we're missing here is all the blood vessels here. They've removed them for simplicity, but essentially the blood vessels would lie over the top of all this. Now, here's your glomerulus. Here's our afferent arteriole. So let's start here. Our afferent arteriole, blood comes in, filters through the glomerular capillaries, blood exits the efferent arteriole. Well, how is urine formed, right? Through the tubular pathway. So here's our capsular space where that filtrate will go. The filtrate will enter this twisty turny area called the proximal convoluted tubule, proximal in reference to the glomerulus. So convoluted means very kind of twisted and turned on itself, right? So proximal convoluted tubule, then we enter this structure. We go down the descending limb, around the nephron loop, and up the ascending limb. And then after the ascending limb, we enter this distal convoluted tubule. And then after that, we enter what's called a collecting duct here. The collecting duct goes through the medulla. Let me see if I can find you a picture. I know there was one in here. Okay. Here's our nephron here. So here's our proximal convoluted tubule, descending limb, nephron loop, ascending limb, distal convoluted tubule. A bunch of distal convoluted tubules are going to empty into this structure, which is called the collecting duct. By the time the fluid gets to this collecting duct, we call it urine. There's going to be a lot of reabsorption secretion in these tubules that we'll talk about in lecture 3. But ultimately, once we get to here, what's in that tube will be excreted as urine. The collecting duct passes through the pyramid here, through the medulla. So those collecting ducts are going to go through the medulla here, drain into the minor calyces. So there's collecting duct coming through this pyramid, where a bunch of distal convoluted tubules from a bunch of different nephrons drained into. Those collecting ducts will fall or drain into the minor calyces, which will merge to form major calyces, which will then go through the pelvis into the ureter, into the bladder. That's the tubular system. Notice how the vascular system is intertwined over that. Why? because reabsorption between the tubules and the vessels happens passively, mostly passively. But they need to be very close so that things can pass between the two systems. All right, so that's kind of our tubular pathway of urine. Let's see here. Okay, so collecting ducts go through the medulla, drain into minor calyces, major calyces, and then out the ureter to the bladder. And this is if it was all stretched out, what that would look like. So here's our glomerulus, and then we can enter our vascular system if we wanted to, which will be intertwined here with all of our tubules and our nephron. And then eventually when we get to the collecting duct and we exit the cortex, we're also venous in the terms of the vascular system. This is going to be venous blood exiting the kidney as well. Blood flow and urine formation happen simultaneously. So as filtrate is being filtered out here, we also have blood circulation happening here. It's clean blood, right? About 99%, in the blood, it is about 99% cleansed after it goes through the kidney, which is pretty fascinating. All right, so in the next lecture, we're going to talk about the three functions of the kidney. We talked a lot about filtration in this lecture. We're going to get more into the reabsorption and the secretion, which happens later down the tubular pathway here.